4 points, one at each corner of a square. 2 opposite corners are blue, the other 2 are orange. Try to separate the colors with one straight line. You cannot. Every line strands a corner on the wrong side. The labels alternate around the square. This is XOR, and in this original space, no single street boundary can split the 2 classes. A network can get past this by changing the representation before making its final decision. Between the input, where the points enter, and the output, where the answer leaves, the network computes an intermediate layer. That internally computed in-between layer is called a hidden layer. Zoom in on one unit. It multiplies each value from the previous layer by a learned weight, adds the products, and adds a bias. Then, the total passes through one more operation before moving on. Hold that final step for a moment, because first we need to see what goes wrong without it. Multiplying by weights and adding is a linear calculation. A linear function of a linear function is still linear. Stack several purely linear layers and they can collapse into one linear transformation. However tall the stack becomes, its input-output relationship remains linear, so it still cannot separate those 4 XOR corners. That final step is the escape. Before a unit's result passes to the next layer, it goes through an activation function, a nonlinear transform. ReLU is one example. If the input is negative, output 0. Otherwise, pass it through unchanged. Draw it as a flat line that bends upward at 0. That bend prevents the layers from collapsing into one linear rule. Now return to the square. Send the 4 corners through a nonlinear hidden layer, and each point receives new values, a new representation. It is like redrawing the coordinate grid beneath the points so a hard boundary becomes simple. In those new coordinates, one straight line can separate the classes. But literally, the layer computes a new vector from weighted sums and nonlinear activations. Nothing bends, numbers are recomputed. Those hidden values are learned intermediate features, coordinates that help the network's objective. They do not need human-readable names, and one hidden unit does not have to correspond to one recognizable concept. It only needs to contribute something useful to the representation received by the next layer. So why stack layers? A feed-forward network composes functions. Each layer's output becomes the next layer's input, and the length of that chain is its depth. In principle, one hidden layer with a suitable nonlinearity and enough units can approximate a broad class of continuous functions. But that statement is only about capacity. It promises no small network, easy training, generalization, or correctness. Depth offers another route. For some function families, deeper networks can represent a transformation compactly, while shallower networks need exponentially more units. That does not mean deeper is always better. Without nonlinearity, extra layers still buy no additional expressive relationship. Everything remains linear. So a hidden layer is not a box of thoughts. It is arithmetic that rewrites an input into a more useful representation. Weighted sums recombine values, nonlinear activations prevent a linear collapse, and successive layers compose those changes. The next question is how training discovers weights that make the representation useful.